Throughout engineering design 1 and 2, our team is building an underwater communication modems, one optical and one acoustic, to support wireless communication for our knifebot. The system is designed to switch between optical and acoustic signals based on real-time water conditions. Since optical works best for fast, short-range data, while acoustic communication is better for long-distance or murky environments, by combining both systems using smart decision logic, the knifebot will maintain a stable and reliable connection with the surface buoy. This multimodal approach ensures strong performance in an environment where a single communication method would normally tend to fail. Underwater communication is pretty challenging because normal things we use every day like Wi-Fi or Bluetooth don't work in seawater. Radio waves weaken almost instantly and we can't rely on the usual wireless methods. That's why underwater systems mostly use acoustic signals or optical signals instead. Uh, acoustic acoustic communication can reach for a distance, but is slow and sometimes noisy, and optical communication is much faster, but it only works for short range and in clear water. Because each method has big limitations, underwater systems still struggle with low bandwidth and reliability. That's why our team is looking at a multimodal solution, which takes both methods together to make communication stronger and more efficient. The main subsystems for our project are the mode switching module, optical module, acoustic module, buoy communication interface module, data handling, and error checking module. These are the key pieces that make our underwater modem work, and we'll get into more detail on each one in the next few slides. Here we have the mode switching module. This subsystem is responsible for deciding whether the knifebot should communicate using optical or acoustic signals, and whichever one it chooses, it switches to that specific signal. First, it includes our software design logic, basically the if-else rules that will compare clarity and distance value. We also have a small table to store the limits that tell us when optical communication is still usable and when we should switch to the acoustic. The mode handler then activates the correct communication module based on these conditions. We have these components because they allow the system to automatically pick the best reliable communication method without manual input, which is essential for underwater environments that tend to change constantly. In terms of interfaces, the module receives clarity and distance readings from the sensor system and sends commands to either the optical or acoustic module, depending on which mode is being used. The main challenges here is determining stable cutoff values for switching modes. We want the system to react quickly but not switch back and forth constantly. For our prototype, we will test different switching strategies and implement the basic logic to evaluate what works best in simulated water conditions.
Our proposed solution for the Knifebot is to implement both an optical modem, the Luma XUV, and the acoustic modem, the Popoto PMM4511, through one microcontrol unit and achieve the best of both worlds in terms of underwater communication, where the microcontrol unit will take outside environmental data such as clarity of the water, light sensing, any kind of contaminants in the water that make it murky, and decides which modem is best for operation. It also accounts for the distance between two knifebots, as the optical modem is better at shorter distances and can transmit a lot more data than the acoustic one, but relies on said clarity of the water as well as any kind of light, external light levels. And the acoustic modem can transmit a lot further but also a lot slower. So our proposed solution is to combine these two systems and decide which one is best for which scenario. This will enable knifebots to efficiently transmit information between each other, allowing them to be used in in-depth research applications such as environmental exploration, monitoring underwater infrastructure, installing of underwater communication lines, and so much more. A block diagram of our system includes the two modems, as well as a battery with converters for each part of the subsystem to allow the entire system to work remotely outside of any kind of additional power sources or input, meaning that it can be completely integrated into the knifebot, as well as the modems connected to the microcontrol unit through Ethernet cables, which allows it to very efficiently and very quickly transmit data between the MCU and the modems, and enable us to give the modems instructions as well as receive information from the modems and transmit it back into the MCU system. The modems will be connected by Ethernet that allows for system data transfer between them and the MCU. And potentially we are also going to add a system where through the MCU and one of the modems we will be connected through a control box, which will be connected to either a buoy or a host laptop that will connect us, the user, to our system, allowing us to wirelessly transmit any kind of information or receive any kind of information that we need out of this system, and make changes to the settings, receive any kind of important information that we need, check the battery life, things like that. So that is another implementation of the system. That was the hardware. So talking a little bit more about the software communication system itself, our protocol includes receiving commands from the surface station or buoy through that control station that I just described, turning on the modems and doing an environmental check to see the conditions of the water, choosing which modem will be active based on environmental location as well as the other location of knifebots, transmitting the data between the knifebots, and transmitting data back to the surface station. And this will all be done through, as we mentioned, the modems, through optical data transfer or acoustic data transfer. The reason why we're not using something like RF or Wi-Fi is because it dissipates very quickly in water, meaning that these are our best sources of communication. And it is definitely a struggle underwater communication, as we cannot just simply stick an antenna on something and transmit whatever signal we want and receive it. We have to be very specific and very careful about how we do it, because signals attenuate very quickly in water, especially ones that are electrical signals, as water is significantly more conductive than air. So doing stuff through different means of communication, such as acoustic or optical, makes the most sense for us. So this is why we are doing it the way we are. Lastly, we have the components of the system, which I had briefly mentioned, some of them, including the knifebot itself, the buoys, the Teledyne Benthos buoys, the Popoto PMM4511 modems, which are the acoustic ones, the Hydromia Luma XUV optical modems, which are the optical ones that are both going to be integrated, a microcontrol unit, which will either be a Raspberry Pi or a RISC-V dev board, which essentially we just need Linux in order to run the APIs that handle our communication protocol, as both modems directly handle through APIs, which means it is through APIs, which means it is very simple to retrieve information from them and do whatever we want with them, like any kind of changes and stuff like that. So we just need some sort of API, and Linux is the easiest to implement. So depending on how much we want to look for future development, we will be either using a Raspberry Pi or a RISC-V dev board, the battery and power converters, as well as Ethernet cables.
Optical module. To justify the optical module, we chose the optical modem because it gives us fast communication when the water is clear. It can send data much faster than the acoustic modem as well. So whenever the knifebot is close to the buoy, the optical sensor will be the best for it. The optical module connects to a Raspberry Pi, which handles switching between both optical and acoustic sensors. Once the Pi receives the optical module, it then sends it to the buoy, and the buoy sends it to the surface. All of this happens inside of the waterproof enclosure where both optical and acoustic sensors sit in. The main issue with the optical is that it only works well in clear water. If the water gets a little bit cloudy and the light signal drops fast, so keeping the lens clean and sealed in a waterproof case is another challenge. Another challenge is we don't know how stable the optical sensor will be when everything is moving underwater. For the first prototype, we are focusing on getting the optical modem powered on and talking to a Raspberry Pi and sending simple signals during bench test. After that, we will place it in a waterproof enclosure and test it with the buoy. Challenges facing the optical module. Known challenges are ambient optical noise, that being sun reflections, LED leakage, and light glimmer acting as noise sources, lowering signal clarity, bubbles and hull wake obstacles. So air bubbles fully block light, causing flickering packet dropouts. We also have short effective range. So optical systems are high rate, but typically short distance compared to acoustic, so it won't serve well for long distance. And under unknown challenges, we have the Doppler effect when the knife ball is moving. Under early implementation for the optical module, we have building a diagnostic logging tool using Python or MATLAB that logs packet success and failure, range pings, signal to noise ratio, and decode latency. We also have plot, which will plot range, packet success percentage, link status, decode delays. We have real-time visualization dashboard, so displaying a time series graph for a range, packet error indicators, bench test rig to vary water clarity and alignment, waterproof mount exposing the Luma X optical port to the water.
Hello everyone, this is Mario Rodriguez. I'll be going over slides 13, 14, and 15. This section covers our acoustic model, and I'm going to do going over four things to justify our components choices. Describing how the acoustic system interfaces with the rest of the project, identifying the main implementation challenges, and indicating what we are implementing in the early prototypes. Firstly, we will justify our primary acoustic component, which is the PopGo modem, the acoustic modem. We have selected this device because it supports bidirectional underwater communication and gives us flexibility depending on the range and link conditions. For longer range reliability, we can use lower data rate mode like frequency hopped FSK, and we can reduce range and improve channel quality. Um, we can move forward towards higher speed modes such as PSK, reaching up to about 10,000 BPS. The point is that it gives us a practical, field-ready acoustic link that we can tune for our testing environment rather than building for a full acoustic modem from scratch. Alongside the modem, we're also using Teledyne Benthos buoys. These buoys are important because they let us run separate, repeatable, distance-based tests. In other words, we can set controlled spacing between buoys and our multimodal unit, measure performance like throughput and reliability at known distances, and generate results that are consistent and comparable across trials. We also incorporated hydrophones as part of our acoustic testing and analysis workflow. Hydrophones allow us to observe acoustic channels more directly, which supports signal processing tasks such as evaluating noise levels, interference, and wavelength clarity. The goal is to bring that data into LabVIEW so we can visualize and interpret what's happening during transmissions. This helps us validate whether issues come from environment, the transducer's path, the configuration in modems, or the way we're handling the data upstream. Um, because of the acoustic module not operating in isolation, our full multimodal solution will have three main components that we can use together. Through the source, or through the software, primarily Python, C++, with the analysis and monitoring performed through LabVIEW scripts. The first of our components that we will be utilizing is the KnifeBot. The KnifeBot is an end user to receive data, meaning it's transmitted information back and forth and uses it to operate accordingly. From the system's perspective, the acoustic module's job is to help ensure the KnifeBot can still receive essential information even when optical conditions are not favorable. The second component is Teledyne Benethos buoys, which do act as a mediary connection. It is essential to our operation as a bridge for bidirectional signaling and controlled testing. The buoys layer also helps us structure the system more realistically because in underwater applications, you typically need some type of gateway or intermediary to link underwater communication with topside monitoring and logging. The third component is our constructed multimodal hardware unit, which physically holds the coordinates of the acoustic and optical modems so that they can work synchronously. As we integrate, the idea is that the systems can choose for the best link at the moment. Acoustic specifically when range is longer than the water, acoustic when ranging for longer or water being more turbid. We would do optical when conditions support high speed, short range transfers. The hydrophone supports this by improving our ability to evaluate signal quality and interpret what channels are doing at real world tests. Now, challenges, especially known and unknown, are practical issues more so that we've faced in test readiness, specifically power and cabling constraints that can slow down, bring up, and field experiments. Beyond logistics, the technical challenges are tied to underwater acoustic channels itself. Link can be affected by environmental noise, multipath reflections, and changing propagation conditions. From a system angle, we have we have to manage reliability, message delivery, so we have to carefully configure modem settings and implement the right communication behaviors in the software, such as structured packet handling, timeouts, and retries when appropriate. Finally, what we have implemented or will implement in the early prototype are establishing stable two-way communication using the POPCO acoustic modem, running distance-based trials using the Teledyne Benethos buoys to quantify performance, and then collecting and visualizing data using LabVIEW, including diagnostics that help us interpret link quality and system behavior. In summary, the acoustic model gives us reliable long range is a long range reliable backbone for communication. The buoys enable controlled and repeatable testing, and the hydrophone plus the hydrophone, and then LabVIEW allows us workflow essentially to observe and infer data from there, um, which is critical for validating the information being produced from the multimodal system as a whole.
Hello, my name is David Osemene, and I'll be going over the acoustic module. The acoustic communication faces three main challenges, which are latency, noise, and physical reliability. Because the acoustic signals move through water and then pass through several stages, which includes transducer detection, amplification of the analog board, digital conversion, signal processing, package decoding, and finally delivery to the robot controller. There can be delays, which makes the system unsustainable for real-time control loops. The underwater environment also introduces noise from pumps, motors, turbulence, and reflections that may obscure the signals. Finally, waterproofing and cabling must be done carefully because stress or changes underwater can stress the physical connections and reduce reliability. For the early prototype, we plan to begin development using both hardware and software. The goal is to quickly validate that our modem can send and receive data in a controlled tank before full development. For the hardware implementations, we will power the modem using a regular 12 to 40-volt fuse power supply to protect against high power acoustic transmissions. We will begin testing waterproof cables, features, and mechanical mounting for the transistors. For the software implementations, we will build a simple login tool in MATLAB or Python that tracks packet success failure rates, rage pings, signal clarity, and latency so we can visualize link reliability early. This lets us characterize the system behavior before writing complex acoustic processing layers. Now let's dive into the BU communication interface. The knife port includes a surface BU communication relay to bridge underwater communication with remote users above the surface. For the subsystem, we selected a BU processor and a wireless transceiver to relay acoustic data upwards without requiring a wired surface connection. We'll use the Raspberry Pi OS environment on the BU to prototype message routing because it lets us quickly implement wireless communications without underwater signal hardware complexity. The BU communicates indirectly through the knife port's main controller, receiving packets that already includes modem diagnostics and the robot's address metadata. The challenges we identify here include maintaining a stable wireless connection above the surface and maintaining interference. For the prototype, we will test a basic packet relay between the buoy and the laptop to verify reliability before expanding the system to multiple nodes. For data handling and error checking, we'll use a data queue, parser, and error checking routing in the controller to ensure packets don't crash the system when traffic increases. The module interacts with all sensor chains, including optical and acoustic, to ensure data is timestamped and errors are caught on early. The main challenges here is preventing overflow or miss errors when packets arrive too fast. For our early prototype, we'll simulate different test packet errors to confirm the controller flags them properly before full implementation. For our syntax, our teams is split into two focus groups, one handling the optical communication interface using the Luma X, and the other responsible for the acoustic communication with the Popo 2 4511 modem. Each group will independently research modem performance, underwater waterproofing methods, and integration with the surface relay buoy. Both teams will establish modem to buoy pairing, system addressing with the Nightbot, and conduct early submersion tests to validate link reliability under real underwater conditions.